Hey, chemistry, how you doing? We're jumping into another flipped lecture here. Now, this is going to be a little bit of a different thing. We've been talking about states of matter for a long time, and here we're jumping into thermochemistry, a whole new unit, whole new concept. For the next several weeks, we're going to be looking at energy of chemical reactions and how does energy flow during a chemical reaction. And before we look at how they flow in a chemical reaction, we have to look at the energy that is present or latent within a material. And so that's kind of what we're looking at today. Thermochemistry is the name of the unit. Let's jump on in. Here we go. So basic terminology here. Thermochemistry is the study of the interactions of matter and thermal energy. So remember the kinetic molecular model of matter, that everything is particles in motion. So the faster things are moving, the more kinetic energy they have, and the best way that we can figure out kinetic energy on a molecular level is by taking its temperature. Thermal energy is kinetic energy at the molecular level. So thermochemistry is the study of how matter gets to move faster or slower at the molecular atomic level. Thermal energy is measured in joules, and this is something that we've done already in physical science, and you will do so much with in physics next year. This is just kind of keeping this alive in your brain. And if we are talking about a lot of energy, we're going to use kilojoules. So joules is the standard unit of measurement. 1,000 joules is a kilojoule, and you will see that unit of measurement a lot. The total thermal energy of a system is called its enthalpy. Now, you saw that word already when we were talking about solutions. The enthalpy of solution is how much heat energy, how much thermal energy is given off when a solution is formed. We're going to use it the exact same way here, but we're looking, instead of just at the process of solvation, we're looking at the enthalpy of making a material. So the amount of thermal energy in a system or in a substance is called its enthalpy, okay? Enthalpy, the amount of thermal energy. And we use the capital letter H for enthalpy, and we'll use it all through chemistry that way, and we'll use it in physics that way as well. So enthalpy is the heat latent in a system. Okay, thermal energy, which changes the temperature of a system, is called sensible heat. You can sense it. If I were to take some of my coffee here and I were to pour it back into the carafe that it came out of. By the way, chemistry students a couple years ago bought me that mug. Love it. So if I were to pour that coffee back in the carafe it came from and heat it back up again, I'd be adding thermal energy to it, and its temperature would go up. That's sensible heat. But if I kept adding more thermal heat, at some point, it's going to reach the boiling point, and then I'm going to keep adding thermal energy to it, but its temperature is not going to go up anymore. It's just going to boil. Whoa, what do you call it when thermal energy goes in, but its temperature doesn't go up? You call that latent heat, because the heat is going in not to raise the temperature. The heat is going in to expand the molecules from each other and move it into a new phase, and it's going to be boiling. So the thermal energy that causes a phase change we call latent heat. Latent means back there hiding. I can't see it. Sensible means there it is. I can sense it. So if you can tell the temperature is going up, it's sensible heat. If you can't, and the heat is doing something else, we call it latent heat. The two most common kinds of latent heat are latent heat of fusion and latent heat of vaporization. Latent heat of fusion is the heat change when something is melting or freezing. Latent heat of vaporization is the heat change when something is boiling or condensing. Okay? Obviously, more heat going in, a positive change in heat would be taking something from a solid to a liquid and then from a liquid to a gas. A negative heat of vaporization would be going from a gas down to a liquid. How much heat does that give off? Or going from a liquid down to a solid, how much heat does that give off? That would be a negative heat of fusion. Okay, there's some symbols there for you. The delta H, delta, remember in science, the capital D means change in something. So this is change in enthalpy of fusion, change in enthalpy of vaporization. And we always measure these in kilojoules per mole. Okay, kilojoules per mole. All right, picture. If I take ice and I add 80 calories, the calorie is the English unit of heat, not the SI unit of heat, but this picture works anyway. If I take ice and I add 80 calories to it, I can take it from ice to 0-degree water. That's latent heat of fusion, okay? And then I can add another 100 calories and take it from 0 to 100 Celsius. This is 1 gram of water. Okay, and then I add 540 more calories. The temperature doesn't change. It's still 100 degrees, but then it gets to be 100-degree steam. And so that's latent heat of vaporization. Going the opposite direction, all the same amounts of energy are needed to take a gram of steam and turn it into a gram of ice. Okay, so at these measurements, the 80 calories and the 540 is the heat that is required to change the phase. The temperature doesn't change, but the phase does. This is a graphic representation of that. If I add heat and this is temperature, sensible heat is when I'm adding heat and the temperature goes up. This is latent heat when I'm adding heat and the temperature does not change. Then it heats again in sensible ways and the temperature goes up. Then I add more heat and it's evaporating and it is not changing temperature. Then I can take steam and I can get the steam even hotter, superheat the steam, and the steam will get hotter, and the more heat I add, the hotter it gets. But it's going to keep being sensible. So these are sensible windows, and this is latent. Okay? Moving on. Specific heat. This is a term that refers to how much thermal energy do I need to add to a substance before its temperature rises. Some substances you can add a whole bunch of thermal energy to, and their temperature doesn't actually change all that much. Other substances you add very little thermal energy to, and their temperature changes greatly. And the difference is their specific heat. How much heat do they need to change their temperature? So we will call that C sub SP, and that's specific heat. Why C for heat? I don't know. But SP helps you specific, right? Specific heat. And there's a formula for this. Q is the amount of thermal energy, similar to H, but different. This is the amount of thermal energy, Q, that it takes to raise a mass of a substance times its specific heat a certain amount of degrees Celsius, or sorry, Kelvin, degree Kelvin. So thermal energy is mass in grams times the specific heat times the change in temperature. Higher specific heat means more energy per degree Celsius. So for example, water has a very high specific heat. You've got to dump a lot of thermal energy in the water to raise its temperature. That's why water heaters are so expensive. If we could all take a bath in aluminum, that'd be gross, but it would make aluminum heaters a lot cheaper because aluminum has a very low specific heat. Dump just a little bit of thermal energy in and it's warm. Okay, so the amount of thermal energy it takes to raise the temperature of 1 kilogram of gold versus the amount of thermal energy it takes to raise the 1 kilogram of water is very, very different. If you put the same amount of thermal energy in, you could get a kilogram of gold to go from 20 degrees Celsius to 90. You put that same amount of thermal energy in to a kilogram of water and it's just going to go up a few degrees. Okay, specific heat. How much thermal energy does it take to raise the temperature of a substance? This is why if you're making soup, you should make a soup with a wooden spoon. If you have a metal spoon has a very low specific heat. You can add the thermal energy from the soup, goes right up the handle, the spoon gets hot, it burns you. Wooden spoons have an incredibly high specific heat, and the thermal energy goes into the wood, and the wood doesn't really get much warmer. Okay, so here's some specific heats, and you can see water has a much larger number than aluminum or concrete or things of that nature. Okay, so the larger the specific heat, the more thermal energy it takes to raise its temperature. Let's do an example problem with this. And my picture is in the way. Let me just show you. It says material and then aluminum up here. But we're looking at specific heats to common materials. Okay, and I'm going to bury that again. If 0.58 kilojoules of heat energy is added to 23.0 grams of ethanol at 13 degrees Celsius, what will be the final temperature? So I need to just do a little bit of math. Here's my equation. No, not yet. From the table, ethanol has a specific heat of 2,410 joules per kilogram. So it takes 2,410 joules of energy to raise 1 kilogram of ethanol 1 degree Kelvin. Or you shouldn't say degree Kelvin, 1 Kelvin. Okay, we have 0.58 kilojoules and 23 grams, but the constant is not given in those units, so we have to convert. So 0.58 kilojoules are 580 joules. okay? And the, because that's joules per kilogram, right? And 23.0 grams, I need to be in kilograms, so 0.023 kilograms. Here's my equation. Oh, sorry, the T should have been over here. Q equals MC SP delta T. Sorry about that. So if I put all that together, 580 joules, 0.023 kilograms, and 2410 is my value for CSP. Then I just am looking for this. Multiply across and solve for T. And my temperature change is 10.46365 degrees Celsius. You've got to remember my significant digits. I only have 2 significant digits, so 10 degrees Celsius. So it was 13 degrees Celsius. Now I'm going to be 10 degrees higher. It was 13 degrees Celsius, so the final temperature is 23 degrees Celsius. Oops. 23 degrees Celsius. So it raised the temperature 13 degrees, 10 degrees. Okay? All right, moving on. Enthalpy of reactions. We're looking now at what's the energy change in a reaction. Balanced equations that show the amount of energy absorbed or released, and we call those thermonuclear equations. If they show you not just the substances moving around, but they show you the kilojoules moving around as well, where is the heat, then we call that a thermonuclear equation. Don't worry, nothing's going to explode. No more Hiroshima or Nagasaki for us, even though we live in Pearl Harbor. But the idea here is we're tracking the energy through the reaction, okay? So we have delta H for the reaction equals the heat of all of the products summed together minus the heat of all the reactants. So if I wind up with a negative value for delta H, then I call that exothermic. What that means is that the products minus the reactants had more energy. They gave some of it off when they formed the product. So my value for delta H is negative. That's exothermic. Positive values for a delta H would be endothermic. The products have more energy than the reactants did, so they must have absorbed some energy in the course of the reaction. Okay. Most compounds have an accepted value for their enthalpy of formation, how much energy it took to make that thing. Okay. The thermal energy present in 1 mole of that compound at standard condition. That's the enthalpy of formation. You can look that up on a table. I will not make you calculate the enthalpy of formation right now. Later. So we compare the energy of all the component substances in the products and the reactants, and we just do some subtraction. The value of delta HOF, the enthalpy of formation, is usually a negative number because most of the time a compound is more stable than the elements it was formed out of. So there are some exceptions to that, but most of the time not. So you're going to be adding up negative numbers and subtracting negative numbers from negative numbers. It's just which one is more negative is the what matters. Okay. There's table 13.7 in your book that will give you all of the enthalpy of formations that you'll need. All right. Let's do some examples here in just a moment. To calculate the delta H, we sum up all the values for the products and all the values for the reactants, and then we subtract them, right? So delta H for a reaction is the sum of all of the heat of formations of the products minus the sum of all the heat of formations for the reactants. Let's do this. Okay. For our lab last week, I had to make a solution of ammonium chloride from HCl and NH3. And I want to know, was that reaction endothermic or exothermic? Did I have to put heat energy into it, or did I get some heat energy out of it? Well, let's find out. Let's look at the reaction. It's NH3 plus HCl gives us NH4Cl. That's the reaction I performed. We need to look up the heat of formation values for the components. So we're going to go to a big table, big nasty table, and we're going to look them up. And hydrochloric acid is right there, negative 92.31. Remember, almost everything on this table is negative. Ammonia, NH3, is negative 45.9. And what I made, ammonia chloride, is negative 314.4. So these are in heat of formation, kilojoules per mole. I get out these many kilojoules by making 1 mole of this thing. Okay, so take those values back, write them down. I'm going to use those. Pretty simple. Sigma delta H of the products minus sigma delta H of the reactants. So the reactants are things I have to actually add together. I only have one product, so I don't have to add up any products. Delta H is the product, this one right there, minus the sum of my reactants, these two. Add these two together. Negative 92.31 plus negative 45.9 is negative 138.21. Now this is a negative number minus a negative number, and minusing a negative is addition, right? So negative 314.4 plus 138.21, my answer is negative 176.19 kilojoules. Because it is a negative number, that means that I have given off heat in the course of this reaction. And so it's exothermic. Energy was released. And I gave off 176.19 kilojoules of energy per mole. And when I made this, it did get hot. I was doing the reaction, and the vessel itself got hot. And I remember thinking, wow, that's really warm. It's giving off a lot of heat. So this is a significant amount of heat that you could definitely detect as you're making the compound. Okay, that is it. If you have any questions, let me know in the comments field below. Otherwise, I will see you tomorrow in class. Jesus loves you, and so do I.